Hello, my name is Lapides. I'm with Imperas Software. And my topic today is why wait for hardware to start RISC-V software development? The agenda today will be an introduction to Imperas. I'll talk about RISC-V, why use RISC-V, adoption challenges of RISC-V, then talk about virtual platforms for software development, the requirements for virtual platforms. I'll present a case study and then summarize. So let's start off here with a brief introduction to Imperas. So the Imperas founding team has a background in electronic design automation tools, as well as FPGA and processor IP companies. We saw the need for tools and methodologies similar to EDA, but for software debug, test, and analysis based on software simulation. So just as no significant simulation, and with verification tools on top of simulation, we believe that the embedded community is evolving so that no embedded system will be shipped without significant simulation-based verification of software. One of the key differentiations for Imperas is that our products have been architected from the tools requirements down, not from the modeling requirements up. So we've built these tools, this environment, based on an understanding of what users would need for software debug, for software analysis, optimization. But also with the introduction and adoption of RISC-V, Imperas has added DB technology and methodology to our portfolio. And in the previous SEM-Israel seminar, I talked about that RISC-V DB technology. Today, I'll be talking about the software development side of things. Just a bit of background on Imperas and RISC-V. We started looking at RISC-V in 2016, Design Automation Conference, and it looked academic and fragmented. 6 months later, at the RISC-V workshop at Google in Silicon Valley, with 350 attendees, the instruction set architecture, the ISA, looks to be converging. We then joined the RISC-V Foundation, built our first model. We started participating in the compliance working group, built more models. We introduced methodology for adding and optimizing custom instructions for RISC-V cores. We had our first paying customer in 2018 using our models both for software development and design verification. In early 2019 was the first tape out of a RISC-V based SoC using the Imperas model as the DB reference model. In Q2 of 2019, the first Imperas customer using the RISC-V model with vector extensions for software development for an AI-based chip. Later in 2019, the first Imperas customer using our models for architectural analysis and optimization. And then about a year ago, customer with a massive RISC-V-based AI SoC brought up their chip in the lab within days of first silicon, based on about a year and a half of virtual platform-based software development. This is a partial list of Imperas RISC-V customers and partners. It's pretty interesting here on the user list, including in Israel, NVIDIA networking, the Mellanox team there, using us for design verification, but a number of others, including NXP, Silicon Labs, Dolphin Design, EM Micro, all related to the Open Hardware project. Some others like NSI Texi, a Denso subsidiary in automotive, some government projects, and then partners on the processor IP side, as well as different organizations. So why RISC-V? Maybe start with what is RISC-V and the history there. RISC-V is an open standard instruction set architecture that began in 2010 at California, Berkeley. Unlike most other ISAs, RISC-V is provided under open source licenses that do not require fees. This is just the architecture, not the processor implementation. Unlike other academic designs, which are typically optimized only for simplicity, this one, RISC-V, was intended to be usable and extendable, and those two features are pretty key in RISC-V. The freedom of RISC-V and not the free is why RISC-V usage is growing so fast. This freedom enables domain-specific processing. So RISC-V is growing in market segments where x86 and ARM are not dominant. So we see this in small microcontrollers for SoC management. We see this in vertical market segments such as IoT and AI machine learning. We see it in horizontal. This freedom enables users to develop differentiated domain-specific processors. And RISC-V users now include not only traditional semiconductor companies, but also embedded systems companies practicing vertical integration by developing their own SoCs. Adoption challenges for RISC-V. Feature selection and design choices require serious consideration due to the implications of every decision. So experienced processor teams know the costs associated with every feature. Certainly those costs are in verification, but also every addition, especially the custom features, impacts the software ecosystem. So the cost of a simple added feature can be huge in schedule, in resources, in quality, and unknown to inexperienced teams. Anything custom, of course, changes to the tool chain, to debuggers, and to other tools. And this impacts the porting of existing software and development of new software, operating systems, drivers, firmware applications that will run on the processor. Those changes, of course, impact the software development schedule, which is usually the critical path to SoC delivery. So how can the software development schedule be accelerated? The point here is that silicon without software is just sand. And so what we want to do for RISC-V, if we really want RISC-V to be adopted, is to make sure the software ecosystem, software tools are there and available for users. We all know as well that software requirements are increasing. There's not only the schedule requirements, but also quality, reliability, security, and safety. And then we need to deal with engineering productivity and innovation. There's also a management perspective to this. First, in the predictability of the software engineering task, where management accuracy on software resource and schedule requirements maybe plus or minus 50%. Maybe it's a little bit better than that, but it's certainly not as good as for hardware development. And there's also the software delivery risk. There's probably not as rigorous a testing of software as the hardware because of the ability to do an easier bug fix in the software. But there's still risks to this, and if you're continually doing bug fixing, that's not helpful. Virtual platforms for software development. So what is a virtual platform? This is a simulation environment such that the software does not know that it is not running on hardware. So it's a set of instruction accurate models that reflect the hardware on which the software will execute. Could be one SoC or multiple SoCs or a board or a system. It's a virtual platform. There are no physical limitations. It needs to run the executables compiled for the target hardware, so running the production binaries. Models for the individual components are connected just like in the hardware, same memory map. Peripheral components can be connected to the real world by using the host workstation resources. It's high performance. These are instruction accurate models. And so you're looking at typically 200 to 500 million instructions per second, or booting Linux in less than 10 seconds. And here we show an example platform. This is a Sci-Fi Freedom Unleashed 540. So this is a single core RISC-V and then a quad core processor. So it does initial boot, secure boot with a single core, and then Linux boots on the quad core, and does this actually in 7 seconds. The traditional hardware-based software development, the advantage here is that it has timing and cycle accuracy. It's going to have JTAG-based debug and trace. However, it's hardware-based. It's late to arrive. There's limited physical system availability. If you're using emulators and not a board, emulators are too slow to run enough system scenarios. There's limited external test access, limited controllability, and limited internal visibility to see what's happening in process. You only have the input and the output ports. It's not a white box. To get around these limitations, software is often modified. So you use printfs, you use debug versions of the OS kernels, you provide instrumentation for specific analytical tools, code coverage and profiling, for example. You add in assertions. All these things you add in for debug and analysis, but actually you're going to strip those out in the production binaries. So this modified software may not have the same behavior as clean source code. With the virtual platform, you're going to have earlier system availability. You're going to have easy access for the entire team. You're going to run the actual binaries. You're going to have quick turnaround, comprehensive testing, controllability, so that you can get to the corner cases, so that you can make errors happen. You're going to have visibility, and you're going to be able to easily automate testing. Those are good things to do, but the virtual platform doesn't have timing. So the virtual platform isn't meant to replace the hardware testing. It's meant to make it easier. This is a generic diagram of the virtual platform environment for embedded software development. The key technologies include the processor models, the peripheral models, the platform itself, the simulator engine, and then the software analysis and debug tools. And we'll talk about those a little bit later. The simulator architecture, build these elements separately. You're going to use a just-in-time binary translation technology to translate instructions to x86. The models need to be built using a consistent, well-documented methodology. And then you're going to run quantums, and this applies for single core or multi-core platforms. This is just some detail on the processor model philosophy. Instruction accurate models are just that, instruction accurate. I'm not going to go into any detail on this, but you can go back and look at this slide just to get a better idea of what instruction accurate actually means in practice. So again, the idea here is that the virtual platforms complement the hardware-based software development. Hardware-based is a proven methodology, but it has its limitations. Virtual platform-based methodology delivers controllability, visibility, repeatability, and automation while running the production binaries. So this can be a real nice complementary tool to hardware-based testing, especially to accelerate your software schedule. Let's go into some of the requirements for the virtual platform. Performance. You want to make sure that you don't have extraneous stuff in the virtual platform, because software developers need high performance. If you aren't within a factor of 2 or so of real time, then software developers are not going to use the other tools. You need to have flexibility to work with various third-party tools and environments, whether that's Simulink or Canoe for CAN-based testing and automotive, or various other environments. You need to have extensive model libraries, including support for heterogeneous platforms, whether heterogeneous means RISC-V processors, or even RISC-V mixed with something like ARM processors. The tools need to be non-intrusive, so anything you're doing tool-wise needs to avoid instrumentation of the source code. And this stuff needs to be easy to use. You need to have a good environment. So let's talk about a case study here. And let's talk about an AI machine learning SoC. This is going to have a lot going on here. You're going to have the AI ML accelerator. You're going to potentially have control processors for the AI ML array. You're going to have an application processor for workload management, and then normal SoC management processors for power management, communications management, security management. And then there are the peripherals that they go around this, but from a software development perspective, we're mostly concerned about the processors here. And then remembering again that this can be heterogeneous. These are not going to be the same processors. You're going to have vector processors in all likelihood for the AI accelerator. You might need to boot Linux on the application processor, and potentially microcontrollers for the others. And again, these could be all RISC-V. They could be a mix of RISC-V and something else like ARM. On the AI architecture, here are just some examples, but typically what we've seen is some sort of array of processing elements. And these can be pretty simple scalar processors with some simple vector extensions. There can be vector processors with instruction extensions, and there can be more. And then actually, if you look at this, you may want to configure this so that you're not using the full array, depending upon exactly what the workload is. So you see the potentially a control processor, even a scalar processor, working with these vector processors, number of elements that are going to be used for processing a specific workload. In this case study, working with our customers that are doing AI machine learning development, this is what the Imperas environment looks like. And in terms of the key technologies and differentiators, Imperas has models of ARM, of RISC-V, of MIPS. We have very high quality models. We have the highest performance simulation engine. We have this Slipstreamer API for non-intrusive tools, and then Debug, which again supports the heterogeneous platform, and software verification, analysis, and profiling tools, including OS-aware tools. On the processor model side, there's a lot going on here, specifically for RISC-V. There are envelope models or generic models of the specification. There are vendor-specific models for Andes, Sci-Fi, the open hardware models, Codasip, the microchip, microsemi, Mi-5 models. There are also customer-specific models that either Imperas builds or our customers themselves build based on the generic models, but then adding in their custom instructions, custom configurations. And then we also support all these other features. Note also see on the system's native interfaces. So we work in different environments, and models are open source. The Imperas environment also supports peripheral models. There are hundreds of peripheral models available in the Open Virtual Platforms library. Again, the models are open source under the Apache open source license. All models, again, have both C and System C interfaces. There's a productivity tool to enable easy building of the peripheral models. One interesting thing is that the Imperas debugger supports peripheral introspection, such as breakpoints on peripheral registers. And this enables things like hardware, software, code debug. So you can do driver peripheral code debug because you have a view into the peripherals. And so, for example, with this AI SoC, that's going to be a plugin into the into a data center using PCI Express. There's the potential to do hardware, software, code debug with that PCIe driver. One of the things that can be done with virtual platforms is to extend the virtual platforms. And there's the concept of an extendable platform kit. This, what this does is provide a known good starting point. So you already have software running, you already have the models. Now you can add the models to customize this to exactly what you're looking for. And we see here in the RISC-V world that we actually have an extendable processor kit for AI ML array of processors. There's also free RTOS on Linux, and I showed the Sci-Fi FU540 virtual platform that's booting Linux. This is something extendable, but also you can have fixed virtual platforms. So these are fixed, delivered as binary only, cannot be extended. It's like a virtual development board. And so this is something for a semiconductor vendor, this is something that can be delivered to your software teams or to your customers' software teams for them to get an early start on software development. I mentioned before the software development tools. This is just showing the Eclipse environment that's used for building that AI ML software environment. They're using CPU and OS-aware tools, including tracing, code coverage profiling, memory monitoring. And users can easily write their own custom tools. This includes assertions. So you can have all the assertions you want in your simulation environment. You don't have to actually put them in your source code. And that means you don't have to strip those out. And then we also this is an Eclipse plugin. And note that any custom features that are added to the processor model are automatically supported by the tools. For this customer, they started software development using the virtual platform with generic models before choosing the processor IP vendor. They use multiple variations of the virtual platform for the different software tasks. They're using a continuous integration methodology. Software development started 1.5 years before tape out. When the chip came back, it came up in the lab and successfully ran the software in just days. Virtual platform worked to accelerate their software development. In summary, RISC-V provides freedom. That's why we're seeing so much momentum in the community. Software ecosystem is key. Virtual platforms can accelerate software development. The Imperas tools meet the requirements for virtual platform-based software development.